Welcome back, everybody, to another deep dive. This time, we have a really interesting listener submission.
Show, yeah.
And it's one that I think we're both kind of scratching our heads about a little bit,
Yeah.
but also super excited to dig into.
A little bit of intrigue.
Yeah, so we have someone sent in a conversation between someone and ChatGPT.
Yeah.
And it's all about the cosmic microwave background.
Right. Yeah, it's not every day that you see someone trying to explain the cosmic microwave background by comparing it to steam condensing on like a glass orb or something.
Okay. Yeah, that sounds pretty wild.
Yeah.
For those who are tuning in, the cosmic microwave background, or CMB,
CMB.
that's that faint radiation that we see coming from all directions in space.
Yeah.
Right.
Yeah, it's like a baby picture of the universe.
Yeah.
When it was only like 380,000 years old.
Wow.
It's one of the biggest pieces of evidence for the Big Bang Theory.
So how are they connecting steam and glass orbs to the CMB?
Well, they're arguing that the patterns that we see in the CMB,
Okay.
like the temperature fluctuations,
Okay.
were caused by something they're calling plasma evaporation.
Plasma evaporation. Okay, I've got to ask, is that a real scientific term?
Not really, no.
Okay.
But
Right.
the way they're using it, it seems like they have a different way of looking at how the early universe changed from this really hot, dense plasma state to a cooler, more structured state.
So we're basically doing a deep dive within a deep dive here.
A deep dive.
So we're looking at how this person is looking at the early universe through their conversation with ChatGPT.
That's right, yeah.
This is going to be good. Where do we even begin with something like this?
I think a good place to start would be by talking about what we already know about the early universe.
Okay.
So we're talking about the period right after the Big Bang,
Okay.
where the universe was extremely hot and dense, filled with this soup of ionized plasma.
Like a cosmic pressure cooker?
Exactly.
Yeah.
And in this kind of energetic environment, light couldn't travel freely. The universe was opaque.
So no observing those first moments directly. We have
yeah.
to kind of piece together the puzzle through things like the CMB.
Yeah, exactly.
Okay.
But then we had this period of rapid expansion, which we call cosmic inflation.
Right.
And this is where the universe expanded exponentially, just in a fraction of a second.
Okay, so we go from this tiny, super dense universe to this massive, sudden expansion.
Yeah.
What happens to all of that plasma during inflation?
So this expansion is really important because it caused the universe to cool down, and that kind of set the stage for this really crucial transition.
Okay.
As the universe cooled, the protons and electrons in the plasma started combining, and they formed neutral hydrogen atoms, and we call that recombination.
Okay, and why is recombination so important in the grand scheme of things?
Well, it let photons travel freely.
Oh, okay.
Before recombination, they were constantly running into charged particles in the plasma.
So the universe went from this dense fog to suddenly becoming transparent.
Exactly.
Right.
And the light that was released at that moment is what we see today as the cosmic microwave background.
So it's a snapshot of the universe at the moment it went from opaque to transparent.
Yeah.
That's pretty amazing. But where does this plasma evaporation idea fit in?
Right.
And how is this person relating it to steam condensing on a glass orb?
Well, they're suggesting that the patterns we see in the CMB,
Okay.
those temperature fluctuations that represent the denser and less dense regions,
Right.
they're saying those are like the condensation patterns that you get when steam cools down on a surface.
I'm trying to visualize this.
Okay.
They're saying the denser regions of the early universe are like areas where the steam condensed more heavily.
Yeah, that seems to be what they're getting at.
Okay.
It's as if they see the CMB as this cosmic condensation record that captured the universe's transition from a hot, chaotic state to a cooler, more ordered one.
Okay. I admit that is a really striking image, even if it's a little unconventional.
Yeah.
But how scientifically plausible is this plasma evaporation idea? Is there any evidence to support it?
That's the million-dollar question, isn't it?
Yeah.
That's what we're going to be looking at throughout this whole deep dive.
Okay.
We're going to look at the details of what they're claiming,
Okay.
compare it to the scientific models we already have,
Okay.
and we'll see if this plasma evaporation idea actually holds any weight.
This is already shaping up to be a fascinating deep dive.
Yeah,
I
yeah.
think we're just scratching the surface here.
I think you're right. This analogy, even though it's unconventional, has definitely raised some interesting questions about the early universe.
Well, listeners, buckle up because we're about to go even deeper down this rabbit hole of cosmic proportions.
Let's do it.
Okay, so we're back. And I'm still trying to get my head around this whole plasma evaporation thing.
Yeah.
It's definitely a new way to look at the early universe.
It is. And I think as we go deeper into what this listener is suggesting, we should keep in mind the scientific framework we already have.
Right.
You know?
Like the idea of quantum fluctuations
Exactly.
in the very, very early universe.
Right.
That always just blows my mind.
Yeah.
These tiny little quantum hiccups basically become the seeds for, these massive structures of the cosmos.
Yeah, that's basically it. Like the current understanding is that those quantum fluctuations got stretched out during inflation.
Yeah.
And that created those density differences that led to galaxies and everything we see today.
So how does this listener's plasma evaporation idea fit into that picture?
Yeah.
Is it compatible with what we already know?
That's what we need to figure out.
Yeah.
One possibility is that this plasma evaporation, if it's real, it might actually complement what we already understand.
Okay.
Maybe those quantum fluctuations not only created the density differences, but they also caused this cascading release of energy as the universe expanded and cooled.
Interesting. So it might not be either thing.
Right.
Maybe this evaporation idea adds another layer of complexity that acts alongside those quantum fluctuations.
Exactly. Think about it. The universe was incredibly energetic and dynamic back then.
Right.
The conditions were so extreme, it could have led to phenomena we don't even know about yet.
Okay.
Plasma evaporation, if it's real.
Right.
Could be one of those.
That's a really cool thought.
Yeah.
But I'm still stuck on one part of this analogy.
Okay.
They keep saying that this plasma evaporation happened before recombination, before the CMB photons were released.
Right.
How does that work with what we know about the CMB's transparency?
That is a great question.
Yeah.
And it shows a possible problem with this analogy.
Okay.
And established science.
Right.
If plasma evaporation happened before recombination, then that means big energy changes were happening inside the plasma, even when the universe was opaque.
But wouldn't that go against how we think the CMB was formed?
Yeah.
We believe those photons were released when the universe became transparent?
Exactly. So if there were these major energy shifts happening before recombination, it makes you wonder how those events would have affected the CMB.
Right.
It's something we have to really look into as we evaluate this idea.
Okay, so let's say, for argument's sake, that plasma evaporation did happen before recombination.
Okay.
What could have caused it?
Yeah.
Are there any clues in our current physics?
Well, we're going into some speculation here.
Okay.
But there are a couple of possibilities that are worth thinking about.
Okay.
The first is that the rapid expansion of the universe could have played a role.
Okay.
Imagine the plasma getting stretched and thinner as space inflated super fast.
Yeah.
It's possible that this stretching could have triggered a phase transition.
Okay.
Something like the evaporation this person is talking about.
So the universe basically growing so fast could have evaporated the plasma.
It's wild, I know.
Yeah.
But it really emphasizes how connected everything was back then.
Okay.
Even space-time itself could have been influencing the plasma.
Okay, that's one possibility.
Yeah.
What's the other one you mentioned?
Well, this one goes back to those acoustic oscillations.
Okay.
You remember those sound waves traveling through the plasma?
Right.
In the early universe?
Yeah.
What if those waves weren't just passive ripples?
Okay.
What if they were strong enough to trigger releases of energy?
Wait, you're saying these cosmic sound waves could have actually changed the plasma?
Yeah.
Like shook things up enough to cause evaporation?
It's a bold idea.
Yeah.
But remember, those sound waves would have been carrying a ton of energy in the early universe.
Okay.
So it's not impossible that they could have played a role in shaping how the plasma evolved.
Okay, I'm trying to keep up.
Yeah.
So we have the expanding universe stretching and evaporating the plasma.
Right.
And we have these cosmic sound waves shaking things up and causing phase transitions.
Yeah.
It's like a cosmic dance
I like that, yeah.
of energy.
And these are just two possible ways this could have happened. There might be others we haven't even thought of.
Right.
But what's important is that this plasma evaporation concept, even if it's just a metaphor, makes us think differently about the forces and energy at play in the early universe.
Yeah, it's definitely pushing the boundaries of what we can imagine.
Yeah.
But I have to ask, if this plasma evaporation really happened, shouldn't there be some other evidence?
Right.
The CMB is only one snapshot of the early universe.
That's a great point if this process was as big as they're saying.
Yeah.
It makes sense that there might be other condensation marks out there.
Okay, now we're talking.
Yeah.
What kind of condensation marks
Yeah.
should we be looking for?
Right.
And where might they be?
That's where things get really interesting.
Yeah.
These remnants could be really subtle,
Okay.
hidden in the way galaxies are spread out,
Right.
or in the properties of dark matter.
Okay.
Maybe even in the fabric of space-time itself.
Wow. So we're not just reinterpreting the CMB. We might be looking at clues across the whole universe.
Yeah.
That's amazing. But how do we even start to look for something like that?
It won't be easy.
Right.
We'll need to come up with new observational techniques.
Okay.
Push the boundaries of theoretical physics.
Right.
And maybe even look at existing data in new ways.
Yeah.
To find patterns we missed before.
So it's a challenge for the whole scientific community.
It is.
It sounds like this plasma evaporation idea,
Yeah.
even if it's not a literal process,
Right.
has really opened up a new area of research.
Absolutely. And that's what's so exciting about this deep dive.
Yeah.
We're not just looking at one person's perspective.
Right.
We're starting a journey of discovery that can help us understand the universe's first moments better.
This is what I love about these deep dives.
Yeah.
Taking a seemingly strange idea
Right?
and seeing where it takes us.
Totally.
And I have a feeling we're not done with plasma evaporation just yet.
I don't think so either. We've set the stage and explored the possibilities.
Right.
But now we need to take a step back and think, what if this idea is true?
Right.
What does it mean for our current models of the universe?
Yeah.
That's what we're going to explore in the last part of our deep dive.
Wow. We've really journeyed through a lot, haven't we?
We have.
This dense plasma of the early universe, this plasma evaporation concept.
Yeah.
We even talked about the possibility of, hidden condensation marks scattered across the entire universe.
Yeah.
I gotta say, this has been a really mind-bending deep dive.
It has been a pretty fascinating exploration.
Yeah.
And now I think we're at the point where we have to ask the big question.
Okay.
What does this all mean?
Exactly, if we entertain this plasma evaporation idea,
Right.
even if it's just a metaphor,
Yeah.
what does that mean for how we understand the universe?
Well, it definitely makes us rethink how simple we think the early universe was.
Okay.
We picture it as this smooth, uniform soup.
Yeah.
But this analogy, with its emphasis on these phase transitions and energy releases, it kind of paints a more dynamic picture.
It's like we're realizing that the baby universe was a lot more chaotic than we thought.
Exactly.
Yeah.
And if plasma evaporation did happen,
Yeah.
it suggests that our models might be missing some details.
Okay.
Like if those energy transitions happened before recombination,
Yeah.
like this person is saying,
Right.
it makes you wonder how those events would have influenced how stars and galaxies formed.
That's a huge implication.
It is.
We're not just talking about a small change to our understanding.
Right.
We might be talking about completely rewriting the early history of the universe.
Exactly. And that's where the real excitement is.
Yeah.
This deep dive has shown us a possible blind spot in our knowledge,
Okay.
something that needs more investigation.
So what's next? Where do we go from here to figure out if this plasma evaporation thing is real or not?
It's a multifaceted challenge.
Okay.
On the theory side,
Yeah.
we need physicists to dig deeper into how the early universe worked, looking at what mechanisms could have driven those phase transitions.
Right. We need the math to back up these cool images.
Exactly. And for observation.
Yeah.
We need astronomers to search for those hidden condensation marks.
Yeah.
Those little echoes of plasma evaporation that might be out there in the universe.
So this is something the whole scientific community needs to work on.
Yeah, it is.
It seems like this deep dive has really sparked a new research direction.
It has, and that's the power of a different perspective. Even one that comes from an unexpected place, like a conversation with ChatGPT.
Right.
It makes us question what we think we know
Yeah.
and opens up new ways of thinking.
This has been a really great reminder that science is all about questioning, exploring,
Yeah,
refining what we know.
absolutely.
And sometimes the most unexpected things can lead to the most amazing insights.
Well said. And to everyone listening, remember, the universe is full of mysteries,
Yeah.
waiting to be discovered.
Right?
Don't be afraid to challenge what you think.
Yeah.
Explore new ideas and keep that curiosity alive.
And who knows, maybe one of you listening will be the one to uncover the next big piece of the cosmic puzzle.
That would be amazing.
Until then, keep exploring, keep questioning, and keep diving deep.
I'll see you on the next deep dive.